what you say. All right. Okay, so units and dimensions. We already talked about that just a little bit. So let's jump into equations. So math is the language of physics. We get these concepts across, and we visualize these concepts that we've been talking about using math equations. So that's where we say that physics, or that math is the language of physics. Much of physics is expressed using an equation. A lot of the concepts we talk about, the laws we talk about, they have an equation to go with them. Okay? So in general, just a reminder to you that in general, an equation is a mathematical expression that represents that relates quantities, physical quantities. And these can be, let me push this up here. There we go. These physical quantities can be properties like length, and they're measured in length, acceleration, speed, and time. So especially at the beginning of this next few chapters that we're going to be looking at, these are the concepts we're going to talk about: length, speed, acceleration, and time. So we're going to be looking at how fast things go, how fast things move from one place to the other, how fast they fall, that would be acceleration, how they can speed up. Okay, that's your acceleration, or slow down, which would be negative acceleration, or we call that deceleration. And all of those are related in an equation. And an equation is just something that relates quantities together. Okay? So that's what you took Algebra 1 for, and Algebra 2, and all that, is to look at how quantities can be related together using an equation. Okay, all right. Okay. This PowerPoint is also, I put this in Schoology for y'all. It is in the day one folder. And I don't have this week's folders up. That's what my free period is for. So I will be putting this week's folders up there today. All right. All right, so here are some examples about using formulas. So to calculate the speed of an object, what do we need to know to calculate the speed of an object? We need to know how far it's going and how long it takes to get there. Okay? So the way we put that in a equation is seen here. So instead of writing speed is equal to distance divided by time, we just write the equation. V for velocity, which is speed. D is your distance, and T is your time. Okay, so if I want to know how fast I'm going at the next cross-country race, what I'm going to do is I'm going to take the distance that I ran, I'm going to divide it by the time it took me to run that distance. And that'll tell me my speed. It'll tell me how fast I'm going. Yes?
Where did you say this thing was?
In the day one folder. Okay. So if you have your little chip reader on your tennis shoe as you're going, that's what it's doing. It's measuring your distance and then your time that it took for you to cover that distance, which is your speed. Okay? Right. It is an average.
You just said we're not going to be going the same speed the whole race.
No, you're not. So speed is the overall average. It's the total distance. That's a good point. It's the total distance covered divided by the total time. Okay. We do at some points talk about something called instantaneous speed or instantaneous acceleration. We'll get to that when we talk about acceleration. And that is the speed and time at that particular second. Okay, so yeah, you're gonna, if you chart that with an app, you'll see that it goes up and down and up and down because your speed is changing over time.
Yeah.
Sometimes you'll pick up and you'll run a little faster, and then you'll get tired and you'll slow down. So that's what we're gonna call, that's an instantaneous, so just at that particular second of time. But in general, we look at from where you started to where you ended up. And that whole distance divided by the time it took you to cover that entire distance, that is your speed. Okay? All right. All right, so any equation can be rearranged, and that's just the things that you learned in algebra. Okay, when we talk in algebra, we say solve for x. That's rearranging an equation. Okay, now you can do it the way you've always done it from algebra, which is probably you took your formula, you put your numbers in your formula, and then you solved for the one that was still there, the variable that was still there. Okay, that's probably how you did it in algebra. Sometimes in physics we do it a little bit differently in that we leave all the letters there. We rearrange it for the one variable we're looking for, and then we put the numbers in last. The end result is the same. It doesn't matter which way you decide to do it, really. There may be times when I will be really mean and I'll give you a problem with no numbers. Here's the formula, because all I want to see is that you can rearrange the formula. Okay? So, in rearranging the formula, it's just do the opposite. It's no big deal. It's what you've always done. Yes, ma'am.
Okay, so I know we talked about like the E squared or E equals MC squared or whatever. So like we had the squared on the bottom. In like an algebra class, that would have been a no-no. Like where do math rules like apply in here?
They apply in here the same.
Okay, so I can't have any of that stuff.
I mean, as far as is that what you learned in math is not wrong, and if you do the same thing in here, I'm not going to count it wrong unless you don't put a unit or you get your significant figures wrong. Those are the two main things that you probably didn't do in math class because it don't really matter as much. That in here they do matter. But if you put in math, what did you have to do? Make that a negative exponent so that you don't have any exponents in the bottom? That's fine. It's not wrong.
Oh, I mean half the time now I forget to do that stuff. So that's lovely.
Oh, but no, I'm probably not going to count it wrong.
Oh, cool.
In that case. I'm not going to get that picky about it. Yeah, I'm not going to get that picky about it. Okay, so here we have this equation, and we are solving for, we're trying to get, wait a minute, let me back up. We're trying to find distance. Okay. All right, so we're just going to rearrange. So I'm just going to give you an example of how we do this with no numbers. Okay, so velocity is equal distance over time. I want to solve for d. I don't tell you any numbers in there. I just say, hey, tell me solve for d. Rearrange this equation is the way it'll be phrased. Rearrange this equation and put it in terms of distance of d. So it basically means solve for d. So what am I going to do? Multiply both sides by t. Boom, 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 boom. So now I have d equals v times t. That's it. Okay. Don't worry, it's going to get bigger. It's going to get harder. But, well, okay. Let me rephrase. It's not going to get harder. It's just going to get longer. It's the same concept. That's the nice thing about algebra and about physics and math. It's the same concept over and over. It just might be a bigger equation. But you do the same thing. What did we do to get d by itself? We did the opposite of what was done. It was divided, so we multiplied. We divided by t, so how do I get rid of it? I multiply by t. Okay, so you always just do the opposite. Okay.
That triangle,
Yeah, you could use, if that helps you remember it, it's that kind of thing. Now, I never learned it that way, so that kind of thing is a little confusing for me. But yeah, you can make that little triangle thing with this. You can do the same thing with density and anything like that. So
Yeah, which one is the heart?
I don't-
What is mass over volume?
that's density.
Okay, so.
So yeah, see, I'm from the old generation. You just memorize it, kind of. So that's like, what? That confuses me. I had to memorize my multiplication tables, all of them. All right, so here we go. Making accurate measurements in the laboratory is an important skill. So when a mass, length, or time is associated with in a scientific experiment, the result is always some uncertainty. So you don't need to write all this down because we're leading up to something else. This inaccuracy or uncertainty we have to account for. Okay? That inaccuracy can be caused by the measuring device. Maybe my balance only goes out to 2 decimal places, and that's it. I don't know what the third one is because I literally can't measure. Maybe it's human error, and that maybe it's 3 decimal places, but that last decimal place keeps flipping back and forth, and I don't know which one it is. Y'all saw that a lot sometimes in lab, that it would just keep going back and forth, back and forth. And you had to guess. You had to say, well, I think it's this. Maybe it really wasn't. So it could be some human perception, and then it could be the skill of the experimenter. When you first came in and you poured something in lab, you never poured it right? You overpoured or underpoured, or so you weren't very skilled in that at first. Okay? So that leads to uncertainty. And we don't like to have uncertainty. We want to make sure that our measurements are as accurate as possible. So let's look at what we mean by accuracy in science. Okay, so accuracy is, you need to write this down, a measure of how close the measured value is to the actual value. Accuracy is how close is my measurement to the actual value. That's accuracy. Versus precision, which is a measure of how close together values in a series of measurements are to one another. So write down those 2 definitions. So accuracy is how close you are to the true value. Precision is how close you are every time you measure it to each measurement. So I could measure the length of this table and get 48 inches. And I could get 48 inches every single time I measure it. Does that mean the table is actually 48 inches? No, because I could be reading it wrong. I could not have a very good ruler. Okay? I could have to guess between 48 and 48.1 or 48.2. Okay? So I'm precise and then I got the same measurement every time. That doesn't mean I'm accurate. I'm only accurate if I am close to the true value. Okay? So the next slide kind of demonstrates an illustration between the differences between precision and accuracy. All right? Are we ready? Okay. All right, so the figure below, hopefully y'all can see that. That circle is not very, can't see it very well. Let's try this. All right, so we got 3 red darts, and they're all within the yellow circle. So is that going to be accurate or precise? It's actually both. Yeah, it's going to be accurate and precise because they're all in the same space and they're all in the right target. Okay, so in this one, here's my yellow circle way over here. And there's my 3 red darts. It's not accurate, but it is precise. Okay? All right, so what about this one down here? Where here is my yellow circle. Here's my bullseye. This is neither. It is not accurate or precise because I'm nowhere near the bullseye and my measurements are all over the place. Okay? And so this one would be what? This one is going to be accurate. They are all inside the yellow ring, but they're not precise. Okay? Because one's over here and one's over here and one's way down at the bottom. Okay? All right, so keep those two definitions in mind. All right, so suppose you measure a distance using a ruler and find that the distance is just over 21 meters. You estimate that the amount over 21 meters is about 0.2 centimeters. So to your best estimate, the distance is 21.2 centimeters. We can say the measured distance of 21.2 centimeters contains 3 significant figures. It's 3 significant figures because I'm sure it's 21 and I'm pretty sure it's 0.2. So there's my 3 significant figures. Definition of significant figures, and you'll want to write this down on the bottom here. So significant figures is defined to be the number of digits that are actually measured plus 1 estimated digit. So the digits that you're sure of plus the last one that you're kind of like, it's somewhere in there. Okay, so that last digit that you're uncertain about, that's the last significant digit you have. Okay. Now, I said in math, we don't ever do these because it's not, or you may do them, but they're just not as big a deal because we're not always doing a measurement. In science, we're actually doing measurements, so it becomes important. Everybody got that? Okay. All right, so now we're going to look at the rules for using these significant digits, okay? When multiplying and dividing numbers, so when multiplying or dividing numbers, the number of significant figures in the answer is the same as the number of significant figures in the least accurate value. So if I were multiplying or dividing 2 numbers together, let's make up 2 numbers. Well, they did one for us down here. So we'll use this one as our example. Okay, so if you want to write the definition, then write this example down. So 21.2 centimeters, and our time was 8.5 seconds. If you divide that out on a calculator, you don't get exactly 2.5. So let's practice that. Sometimes people don't believe me. So let's prove that. So take your calculator, the one on your computer or the one in your hand or close by or whatever. Take 21.2 and divide by 8.5. What do you get? A bunch of numbers, yeah. 2.49411767. I don't want to write down all those numbers. And more importantly, did I actually measure that out to the 1, 2, 3, 4, 5, 6, 7, 9, the billionth place? No, I did not. Okay, so my answer can only be as accurate or as precise, that's a better word, can only be as precise as my least precise number, the one with the least number of significant figures. So how many significant figures should this answer have?
2.
2, because which number has only 2 significant figures? Which of the 2 numbers, here and here, has only 2 significant figures? The 8.5. Okay? So that's 8.5. That means my answer can only have 2 significant figures. So I have to round to 2.5. Okay, does that make sense? Okay. What time did we get out of here? In just a few minutes. Okay. Let's see if we can get one more slide covered. All right, so let's do adding and subtracting, and then I'll give you some practice problems for homework because that's going to be the best way to get these done. So in adding and subtracting, it goes by the decimal places. So in adding and subtracting, the number of decimal places in a result is equal to the smallest number of decimal places. So you don't count the significant figures when you're adding or subtracting, you count the decimal places. And your decimal place in your answer can only have as many decimal places as my number with the smallest number of decimal places. And that is too many times to say those two words in one sentence. So here's an example. So we're going to take 16.74. We're going to take 5.1. We're going to add those two together. So when we add those two together, we get 21.84. But I didn't measure that out to the second decimal place. That's too precise. My answer has to be rounded so that it only has one decimal place. So my correct answer would be 21.8. 21.8. That's to be my correct answer. Okay? All right. So, homework tonight. This is 22. Let's do 23 through 25. No, take that back. Chapter 1, let's do the practice problems on 27, 28, and 29. So that would actually be 23 through 29. Practice problems 23 through 29. I will. It will be on Schoology. 23 through 29. Will be on Schoology and couple hours. Okay? Homework, make sure you put your homework on the end of the table, and I will pass that back to you tomorrow and give you some tape and you can take it back in. Tonight, just take a picture, upload it to Schoology. All right, y'all have a good day. First full week. All 5 days today. All 5. And the next day.
And the next day. And then you can. Not bad.